In this video, I'm going to take you guys through a few of the problems that I gave you in your applications worksheet. I know we had the second set of 1 through 4 in this video. We didn't spend a whole lot of time in class today talking through it, and I might try to get through a couple of the 28 and 29 down there at the bottom. Remember, didn't have to do number 30. All right, so this is an applications to quadratics here. So looking at this first one, the garden problem, I have it set up on the next page here. So in a garden, you decide to plant a bulb garden. Okay, bulbs would just be like little flowers, all right, or the bulb of the flower. You want the length of the rectangular garden to be 3 feet longer than its width. The bulbs that you have will cover 88 square feet. What should the length and width of the garden be? So the best thing here that you want to do is draw yourself a diagram or some kind of a picture that you can follow, all right? So pretend here that this is our rectangular garden. We want the length of the rectangular garden to be 3 feet longer than its width. All right, this is the width here. We don't know that value, so we can call it x. Okay, if that's x, my length needs to be 3 feet longer, so it'd be x plus 3. All right, and then the amount of flowers of the bulbs that we have to cover 88 square feet. Okay, so we can use this information here to set up a little equation for area. And then we're going to have to use factoring and solving in order to find the value of x, okay? So area is length times width. We have a length here. That length is x plus 3. That width is x. And we have an area that we can cover is 88. So that looks like stuff that we've done before in class. All right, so this looks a little bit backwards from what we normally do, but you can distribute it the same way. Okay, so the x goes into both of those. We have x squared plus 3x. And then remember what we had to have it equal to, whatever we did with that number on that side there. So we have to move that over. All right, so it'll be minus 88. So we have minus 88 equals 0, okay, because this would cancel out to a 0 here. After we do that, now we are on to factoring. And you could have used quadratic formula if you wanted to. Just distribute that through there and use quadratic formula, but I think that takes a little bit more work than factoring. So we use a 0 on the left because that's what we have there, and now we have to think of the factoring here. So what two factors of 88 will add to give me a 3? Okay, so 88, that's 8 and 11, right? 8 times 11 gives me 88. So let's see if that works. We have x, let's say minus 8x plus 11, because we want those two factors to add to that positive 3. So do 8 and positive 11, or negative 8, positive 11 add to a positive 3? Sure do. So then zero product property says that I can set each of these pieces equal to 0 and get my solution. So this one down here would give me x equals 8, and this one over here would give me x equals negative 11. Okay, now we are working with area again, so a little number sense here. Do you ever want a negative side length? Because these x's, the values that we solve for, are essentially the side lengths of our rectangle. Okay, area is never going to be negative, so that one's out. So we have x equals 8. And we actually have to know the value of our side lengths, so you're going to plug in an 8. All right, so our area, or our dimensions, would be 8 feet by 8 plus 3 is 11 feet. All right, and we also could have gotten those here and here. Works out the same way, kind of cool. All right, that is number 1. So number 2, let's check that one out. I think that's the dolphin problem. Okay, we have a dolphin. The path of a jump by a dolphin can be modeled by the function right there. That function y equals negative 0.2x, parentheses x minus 10, where x is the horizontal distance in feet and y is the height in feet above the water of the dolphin. Okay, how far does the dolphin travel? What's the maximum height of the dolphin? Okay, so I kind of have a feeling I did the wrong problem here. Let's look and see back at the original here. I did the wrong, let's do this one right here. This is the one we want. Gray kangaroo, that's what we're looking at. That's the one we had issues with in class. So let's really quick put that one on a different slide here. Okay, we're going to take care of this real quick. Get rid of that one, put the kangaroo problem. There we go. All right, let's do the kangaroo one. Okay, so you got the gray kangaroo. He is jumping, and that's the equation that modeled the kangaroo's jump right here. All right, so same kind of concept with the dolphin, but now we're doing a kangaroo. All right, and it's not as easy because it's not factored for you. So the equation that we have there, negative 0.0267 x squared plus 0.8 x is our equation that modeled the distance traveled in feet. Okay, and y is the corresponding height. We just want to know how far the kangaroo can jump. So that is pretty much solving for x. Okay, so you can use the quadratic formula. Negative b plus or minus square root b squared minus 4ac all over 2a. You can use that, or the easier option would be factoring. So remember, factoring is the same as division. Can I divide this by itself? Yeah, you can. So if I factor that out, negative 0.0267, and I can take an x out here too because that's my shared variable. Okay, I want to take an x out. Now, if you divide this by itself, or that, you would get a 1 there, right? Because when we take the greatest common factor out, we divide that out. Okay, so this would just turn into a 1x, and then we have to divide this 0.8 by that negative 0.0267. Okay, so when I do that, you're probably going to want a calculator. So 0.8 divided by negative 0.0267. We get, so that was an x there, deleted, so x minus 29.96. That's what you get when you divide 0.8 divided by 0.0267. Okay, and then since we're solving for x, that becomes a 0. We're factoring, we always want to set equal to 0, and then you get your two solutions. So that, whenever you have a variable in front, we get a 0, and then this one, you're just going to think opposite the parentheses, or again, zero product property. Set it equal to 0 and solve. We get x equals 29.96, and our answer is in feet here. Okay? Then you ask yourself, which one is going to tell me how far that kangaroo jumped? Well, obviously it should be the 29.96 because 0 is the beginning point. 0 feet, he didn't go anywhere, but we know he's jumping. Okay? So 29.96 feet. We don't care about how high, we just want to know how far. So that's it. Okay, that's the second problem. Another application to this stuff. Okay, the parking lot. We're going to make a parking lot. Anything that's kind of square or rectangular, you can use quadratics to figure out dimensions for. Okay, so this one we have a parking lot that's a rectangle. Okay, so we're back to the diagram, rectangle. It's 120 feet by 180 feet. Okay. We want the area doubled by adding the same distance x to the length and width. So if we take this, we add our x to both sides. Okay, x there, that's going to double my area. Okay, so we need to know the area to begin with. That's length times width, 120 by 180. Okay, so the area to begin with was 180 times 120, which is 21,600 feet. Square feet. That's our area to begin with. Okay? So now we need to make our equation for area, and we know that this one is going to be double the area. So, the equation for the length and the width. Length is 180 plus x, or you can do x plus 180, doesn't matter, it'll work out the same. And width is 120 plus x. That's equal to double my area. So we know my area is 21,600, we double that. So it's 43,200. Okay, so now we're going to have to move everything to one side and either use the quadratic formula or factor and solve. So boom, 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 boom. So foil that thing out, and I'm going to just kind of rearrange it while I foil it out. So you're going to have x squared, 120 and 180x, so that's 300, so plus 300x, and then we'll get 21,600. equals that 43,200. Okay, now we need to put everything on the left. X squared plus 300x. And when I move that 43,200 over, I get a negative 21,600 equals 0. So now you got a crazy big number to factor. So quadratic formula might be a better option here. Okay, another option would be go to a graphing calculator, punch that thing in a graphing calculator, and look for the x-intercepts. Okay. So when you actually factor it out, you are going to use 360 and 60. All right. So those multiply to give me 21,600. So we want a positive 360 and we want a negative 60. Then your two solutions here, you'd have x equal to negative 360 and then x equal to positive 60. Since we're working with area again, that 360 is out. So 60 is our answer. And we actually need to know the dimensions of the new parking lot. So x was 60, so we're going to put 60 in here and 60 in here. So my length now is 240 feet and my width is 180 feet. Those are my new dimensions. Okay? And quadratic formula would have gotten you those same, or would have gotten you that 60 again. All right? And then number 4, last one. Oops, it's at the bottom. Number 4 is the one with all the crazy decimals. Okay, let's move that up a little bit. So it's a heat index problem. So here's another application. This could be used for meteorology. All right, so we are trying to figure out a heat index here. So you guys know heat index is like how hot it feels according to the humidity and all that good stuff. The heat index H in degrees Fahrenheit can be modeled by H equals 0.0576 T squared minus 7.588 T plus 319.929. Lots of decimals. It's okay. We can do it. Where T is the temperature in degrees Fahrenheit for a relative humidity of 65% and T is greater than or equal to 70. Find the temperature that has a heat index of 95 degrees Fahrenheit. Okay, so when you're reading it, there's kind of a little bit of fluff material in here because you might think that you're going to use this stuff here. All right, that stuff right there just tells me what temperatures it actually works for. Okay, this equation that we're given doesn't work 100% of the time for every single humidity. Okay, so we're just going to assume that we can use this equation for the information that we're given. We're given a heat index of 95 degrees. What did we say, or where did we say in the equation the heat index was? That is H. So 95 degrees goes where the H is, or just 95. And then we rewrite all that good information out here. $319.929. Okay, so when we factor, remember what we need. 0 over here, so let's move the 95 over. If you saw in class today, you saw that little negative 95 floating around up there. That's why. So 0 equals 0.0576 T squared minus 7.588 T. And then we do 319.929 minus 95 gets me to 224.929. And then we are on to the quadratic formula, okay? Some other options, I don't know if I'd recommend, but you can divide everything by 0.0576, and then that would get rid of the number in front, and you can factor it that way, so you'd have to figure out factors of the back number. You can complete the square. Honestly, I think quadratic formula is the best way here. So negative 7.588, so that's opposite b plus or minus square root of b squared. So that's negative 7.588 squared minus 4a is a 0.0576. C is that 224.929 all over 2a. Okay. So it's a lot of calculator work here. You're punching that whole thing in your calculator. So let's simplify it down a little bit. So that is a 7.588, okay, plus or minus. Let's do this one. So square that. So 7.588 squared gives me, and let's round, since we got 3 decimal places floating around in a lot of these, let's use 3 decimal places, so to the thousandths. So this would be 57.578. And then this one, let's do that one. So 4 times 0.0576 times 224.929. That one turns into 51.824. Okay, so now we're doing 57.578 minus 51.824. And that's going to give us the number underneath the radical, or the square root, whatever you want to call it. Okay, so we got 57.578 minus that 51.824. You get 5.75, or 5.74, excuse me. 5.754, that's what it was. 5.754, that's underneath the radical, and on the bottom we got 2 times 0.0576, which gives me 0.1152. Okay, so from here, you're going to have to get 2 answers, so I would just use your calculator again. We have to do once with a plus, because we have that plus or minus, and once with a minus. You have to run the equation twice. Okay, when I do a plus, 7.588 plus square root of 5.754 divided by 0.1152. Our first answer is 86.691. Okay, our second answer, we're going to do 7.588 minus that square root, 5.754, and then divided by 0.1152. That one gives me a 45.046. Okay, those are your 2 answers. Now, going back to that original problem here, you do need that fluff information, I suppose, for the last part of this problem. Okay, because what does this equation apply to? Right here is the piece. It applies to temperatures greater than or equal to 70. Okay, so our heat index would be the number that's greater than or equal to 70, which would be, or our temperature, I suppose. We're solving for our temperature when we have a heat index. The temperature that we have is at 86.691. Okay, to put some number sense to it, think about what heat index is really. Heat index is how it actually feels outside. It wouldn't make sense to say that our temperature is 45.046 degrees, but we got a heat index of 95 or 90, whatever it was, 95, okay? Your heat index is never double the actual temperature outside. So that is the answer that's out. This is the one we're looking for, okay? And if you really wanted to simplify it down, you could say that it's 86.7 degrees. Okay, either one would be fine. Okay, so those are the 4 problems that we needed to cover in class today. And if you have questions on the rest of them, send me an email, or you can try to figure them out. We've actually done a couple of them similar to that in class. Give them a shot. Let me know if you need any help. I can try to help through email or possibly make another video tomorrow. So hopefully this helped. These are applications of quadratics. Okay, so there you go. Enjoy.